1 is the correct first derivative. Check your work. Melina, second derivative for problem 2?
2x.
2x is correct. Anybody with a math question, stop the show. If you have a math question, you can stop the show. Norman, number 5, what's your first derivative?
X squared plus x plus 1.
Alright, x squared plus x plus 1, that sounds good to me. Alec Peters, what's your second derivative for problem 5?
It is 2x plus 1.
Alright, let's put Minecraft away. That is a correct answer though, so 2x plus 1, check your work. These are too easy. Alright, so we'll skip over 8. Let's get to, yeah, let's get to 14. I'll put this aside and get some paper and pencil out here. Caroline, what's your deal with 14?
I got 5x squared plus 10x minus 2x over x to the 4.
Alright, so take me through. So dy dx, and then you start doing your quotient rule or something like that. What'd you start writing?
X squared times 2x plus 5
It's looking pretty solid so far.
minus x squared plus 5x minus 1 times 2x over x squared squared.
So x to the 4th. Yeah, I'm not going to lie, I don't feel like simplifying that right now. I don't want to talk about it. So you can combine like terms and do all that stuff on your own time. Alright, Caroline, I'm happy. Anybody with a quotient rule question? Simplify it on your own. 17 I'm not interested in, that's the same as the other one. 20 was interesting. Rather than calling somebody, did anybody have any clue what was going on with 20? Just any human in the room?
I really wrote no on my paper.
You just wrote no, Melina?
Did you have to actually do the limit h as h approaches
Yes.
0?
So take 28, it's interesting. Limit as h goes to 0, and then you think about x. Okay, so think of x as a function, like y equals x. Okay, so then your inputs would be like x plus h minus x all over h.
And you end up with 1.
Yeah, you do. Because x minus x is 0, you see what I'm saying, Jess?
Oh yeah.
So then you got, oops, limit h goes to 0 for h over h. You can see what I did there with that h. Anyhow, him. And then that's like 1. So what this is, if you accept the limit definition of the derivative, this is a demonstration of the fact that the derivative of x is 1. It's a proof. Okay? So I thought that b was really interesting, so I think I'll just kind of talk about this. Oh, h. At this point, u is not x. U is a function of x. They say negative u, right? Yeah, negative u. So you think of it this like this. Negative u of x plus h. The point here is that u is y, basically. This is how 20b goes down. It's interesting. Does anybody have a question there? That might not even make any sense just at first, like, right away. I don't know. It's a little weird. Again, u is not x. U is y. U is a function of x. Then you do a little bit of math, like this. So you can factor that negative to the front. Oops, that was ugly. My bad. And then I don't know if you remember this, but we had these brief rules. I just told you to look them up in your book. Randy, it was like, if you have a limit of a negative something or other, then you can just put the negative in front of the limit. Does anybody in the room get it now? Can you put any words to this? We're pretty much home. Do you get it? You were asked to demonstrate that the derivative of negative u of x is negative du dx. Does everybody get it? It's a little weird. Yes?
It's like if we were to say u is 1, it's like saying the derivative of y is the derivative of y.
Not exactly, because it was negative y. It was negative y. So it's like the derivative of negative y is equal to negative derivative of y. Maybe this will help, Curtis. Watch this. Ah, now it's so much different, see? This just is the derivative of u with respect to x. It's the limit definition of the derivative. But then there's a negative sign outside of it. And that which was to have been demonstrated. That's it. Bold? Bold? Good? Not good? Nice shirt.
Thank you.
This is alright?
Yeah. Color is it? I don't know. I'm trying to figure that out.
Blue.
Blue. That's what I came to.
Alright, so anyhow, I'm glad I could be of service. Okay, so anyhow, yeah, it's a little wonky, but there it is. Let me see if I'm even interested in any of these. Ooh, yeah, Aaron, I am kind of interested in just let's say 23A. I don't want to talk about all of it, but just what do you think for 23A? What'd you do?
I wasn't sure how to do this.
Alright, but could you give me the derivative of UV? So ddx of UV. What is it? Product rule. You don't have it memorized yet? Let me help you. There's your product rule. I mean, I really haven't even done any math. I'm just sort of writing a rule down that's in the notes. You see what I mean?
So,
But not, yeah, go ahead.
uh,
Do some replacement now.
5 times 2, and then plus negative 1 times negative 3.
Very good. Yeah, that seems pretty sweet to me. Yeah, well done. So then you have 10 plus 3 or 13. So there's 23A. I don't want to do the rest of them, but that was the idea with it. You're given limited information. You're asked to understand the product rule in the abstract. So not like product rule in a context like problems 1 through whatever. So just in the abstract, and then you just plug in numbers. Yeah, it's very good. Anybody with a math question, it's okay to have math questions. We have a sweet lecture today, that's why I'm kind of moving things along. But what are you drinking there, some apple juice? That's just a bunch of high fructose corn syrup or what?
You don't want to know what it is. Real apple juice.
Oh, is that urine? Is that what you're trying to imply?
100% apple juice.
Oh, sweet. Alright, yeah, 23, whatever, 26,
8%
then I'll talk
capacity.
about 29. Ooh,
No.
ooh, 29, that seems kind of spicy. Bands?
I really don't understand how to play 29.
So it says, find the points on the curve, gives you a function, where the tangent is parallel to the x-axis. So alright, we got y equals a bunch of stuff. Sorry, that'll take me a second. So certainly if we're talking about tangents, then we're going to need a derivative. So Vance, go ahead with y prime.
6x squared minus 6x minus 12.
And it says find all points on the curve where the tangent is parallel to the x-axis. What would be the value of the derivative when the tangent is parallel to the x-axis?
0.
0 is correct. So now think about that.
So 0 equals.
Yes, very good. We do a lot of this in calculus. This would be the approach, is you would set the derivative equal to 0. Very good, Banks. Good reasoning. All right, I like it. Darby, any thoughts about solving that? I don't know if you got that far on that problem, but what would you do with that if you wanted to solve for x, Darby?
Factor?
Factoring is a good answer. I like that answer. So maybe we do this. I'm like a factoring machine. All right, Darby, factor that for me.
X plus 1, X minus 1.
Not x minus 1. 1 times 1 is 1, not 2.
Oh, minus 2.
Yeah, x minus 2, x plus 1. Good. So then, Darby, what are the values of x for which the tangent is parallel to the x-axis?
2 and negative 1.
Very good. Very good. I need a calculator. Alright, here goes. This is going to be fun. So I'm going to go up and graph my original. Whoa. Can I delete that?
Yep.
So that would be fun. Alright. Ooh, you You got the old school calculator. Sweet. Because you don't have to press the right arrow after every power. You might want to keep it this way. Some people prefer it. It's an aesthetic choice. You do whatever you want. Alright, so if I graph this now, maybe I do a little zoom fit. Darby, you said at x equals negative, dang, whoa, hey, no, whoa. Alright, let me change that. Those numbers. Do you guys understand zoom fit? Does anybody not? You don't understand? Alright, we're going to talk about it. Before these were negative 10 and 10, it just will fit the graph. It won't change the x values. It keeps those the same and then fits the graph into the viewing window. So now I'm narrowing it up, I'm going to do zoom fit again, and it'll just fit the graph in.
What's the number you press?
You press zoom 0.
Okay.
Hey Darby, you said at x equals 2, the slope of the tangent line is like 0, right? Or the tangent is parallel to the x-axis. Actually, it looks like it is the x-axis maybe. So yeah, and then here at x equals negative 1, same thing. In other words, I'm asking you, do you like it? Does this look good to you?
Sure.
That's not a confident answer. Alright, so the idea is like right here, at x equals negative 1, and then at x equals positive 2, is the slope of the tangent line equal to 0 at those two values?
Yeah.
Yes. Yeah, that's better. I like that better than sure. If you think about sure, it's kind of non-committal. Would you go to homecoming dance with me? Sure. You know what I'm saying? Will you marry me? Sure. It's not ideal. You know what I'm saying? It's like kind of questionable. So anyhow, Darby, that's better. Yes. That's what I like. Yes. Not much sure. Alright, very good. Of course, I'm just joking. Like if you're unsure, you should say things like sure. Or maybe you can say I'm not sure, or things like that. Okay, so anyhow, yeah, that's pretty good though. So these are the values of x. I don't know if in the back of the book they give values of y. We mostly don't do that on the AP exam. But sometimes, I don't know. What you eating there, Peters?
Pretzels.
What? Pretzels. Okay, pretzels. Yeah, I'm all done with all this. So I apologize if we didn't get to everything, but we got a nice little sampling. That was kind of fun. I'm going to need to shuffle these up while you watch a video. I got a sweet video. If you have me for pre-calc, you've already seen this video. But it's an important video. Well, it doesn't hurt anybody to see it again. It's about a moonwalking bird.
Oh, yes.
Jess is gonna watch this and she's like, what the hell?
Yes.
Alright, switch it over, Jess. You got the nerd scientist. She's in the
But with
forest.
high-speed imaging, the secret of their dance can finally be cracked.
This little baby was the breakthrough for my research. It's a high-speed video camera that enables me to record at 500 frames a second. Your average camera goes at 30 frames a second, which means you're missing 90% of what's happening. So with this camera, I'm able to capture these behaviors and play them back in slow motion and just look and see what they're doing.
The big mystery is how these birds make their peculiar high-pitched calls. The images from the high-speed camera show clearly that the sounds come not from the bird's mouth, but from its wingtips. At 80 hits a second, this is quicker than the speed of a hummingbird's wing. A movement so fast, it is invisible to the human eye. And there's more. The dance of the red-capped mannequin has another surprise in store. Kim's knowledge of the bird's ritual is now so intimate, she knows every move.
So, first thing you do is you're sitting on your perch and click, you fly away. Once you're out there, you come swooping in, do a loop-de-loo in the air, land on the perch, and at the end of that, what the males do is they lean over, lift up their tail, quiver the tail slightly, and nail their feathers against their sides. And now you're going to do a moonwalk, and this is the only known case of birds moonwalking to my knowledge. But they basically do these little steps backwards, And it looks like a Michael Jackson slide. It's very nice.
Yeah.
It's so weird.
It's not a school of bird.
If Michael Jackson's
All right,
moonwalk
anyhow, I'm pretty sure I saw that bird touch the ground. It's like you, it's not appropriate. So anyhow, well, I'll probably get a call from Lester later about this. So, but yeah, keep that little bird in mind. We got some work to do. I got a sweet lecture for you. You physics people, your time is finally arrived. For some physics. Okay. So hopefully by this point you get the idea that the derivative is a slope, right, slope of a tangent line, and that the derivative is an instantaneous rate of change. One more?
Yeah.
Need one more?
Yeah.
Here, look up here until it gets back. So basically, derivative, slope of tangent line, instantaneous rate of change, these are all the same. That's the meaning of the derivative. Like all that work we do in the first month is to just get you to understand the idea, like the meaning of it. Okay? So now we're going to start to apply it. It's going to be fun, like physics. So here we go. The simplest like motion that we can sort of conceive of, or is very popular in a calculus class, because it's very simple. It's just motion in a line, like motion of a particle in a line. So like this bird, you eliminate the idea of up and down movement. You just think of it as moving left and right on a straight tree branch, like that kind of idea. So you just have particle motion in a line. Now, is the bird a particle? No, but you know, you get the idea. It's like, think of the bird as like a single location or something like that. And then the idea is that its position is given by a function like of time. So it's very popular to use S for that. I don't really know why. Any of the physics people, you know why? Why S? We have V for velocity, A for acceleration. It makes sense. S. Because the third letter is S in position. I don't even know.
No, displacement.
I don't know either.
S stands for C. Yes.
No. No, that's not it. That reminds me. Are you the one who ate the pie like 2 years ago at the homecoming thing?
Yeah.
Yeah.
Why? Why do you think of that right now?
He's the
You're
one.
thinking of position. I was thinking about you like moving around in that circle.
He was the one that did it to himself.
Yeah,
And you like ate the pie, and it was so weird.
Tomcat was eyeing me up and he was saying stuff to me. I can't say out
So
loud.
it was preemptive then.
I had to, otherwise it would have been.
Okay.
I wouldn't be here.
But is it made out of shaving cream or was it?
No, it was like whipped cream. It was delicious.
Yeah,
It was really good.
It's pretty good.
I loved it.
I should do that next year. Okay. So anyhow, I'm sorry. Let's get back to math. So okay, here's the deal. So position is given by S as a function of time. So that's the position. It's like, where is the bird? Okay? Maggie, let's start with you. What is ds dt? Remember that S is position.
Would that be the position in, or,
No. So the derivative gives the instantaneous rate of change of a function. What is ds dt then, conceptually? What's the instantaneous rate of change of S with respect to time?
the speed?
Close. Velocity. Very good. You're not really wrong, but technically you're wrong. Okay, so it's velocity. That's what ds dt is. The derivative of position is velocity. Very good. Alright, so for our example, let's imagine like this bird. And its position, you could pretend like this is position 0. See what I mean? Like it starts at position 0, and then it's going to start moving around, or that kind of thing. So, all right, Luis, let's start with you. We're going to graph the position function. So give me some ordered pairs. So say if t is 0, what's s? Where is the bird? Kind of already said it. So.
0.
Yeah, 0, right? So Luis, do some arithmetic. Put a 1 in there. What do I get back?
1 and 4.
Yeah, not really 4.
Oh,
Like do it right instead of wrong.
5.
The negative's on the outside. That can be confusing. So this is, you don't put a 1 there and then square negative 1. You put a 1 there, square 1, get 1, and then take the opposite of it.
Oh,
So
3.
3, good, good. Alright. How about for t equals 2?
4.
Good. How about for t equals 3? It's like 12 minus 9.
4.
12 minus 9.
Oh, 12 minus 9, that's 3.
3. Alec Peters, finish this off.
So I'm doing 4.
Yeah, when t is 4, or you can just look at the picture and tell me the answer.
Oh, okay, it's gonna be 0.
Yeah, good, alright. Then how about when t is 5?
Still my turn.
Yeah, arithmetic. Do it.
Okay, so -5.
Yeah, alright, good. Math. Alright, we can connect these with a smooth curve. So this is like where the bird is. Alright, fair enough, we graphed it. Darby, find v of t. In other words, find the velocity function. I'll start you by saying that v of t is the derivative of s. In other words, v of t is s prime of t. That's what Maggie said in the first place. So given s here, Darby, then I need v. In other words, I need the derivative of that, so do it.
-2t.
Good start.
And then
So like here, you can think of this as t to the first. Do 1 times 4. That gives 4. And then t to the 1 minus 1 is t to the 0. What's anything raised to the 0? What's 1 times 4?
4.
So just that. See?
Okay.
Alright, so we have our velocity function. And now a physics question for Jess Conway, of all people, who's in physics. Right? At what time does the bird change directions? Yeah, at t equals 2. Very good.
6:30.
So what at 6:30? Do you want to fight? Alright, t equals 2 is the correct response. Alright, very good. I'm glad we had that talk. So, Darby, what I'd like to do is I'm going to graph this. And it's just a linear function, so I'll do it in a different color. The slope is 2, negative 2, sorry, and like that. Alright, I have a complete graph of the velocity of the bird on the interval. Interesting. So this is where now some of the class, it seems like every year, will just get this right away intuitively, and others will struggle, alright? So Jess, could you explain, like, how did you know that the bird changes directions at time t equals 2?
Well, the graph reaches a peak at t equals 2.
Okay, so the graph reaches a peak.
Also, if we plug in 2 to the equation, we get 0.
Okay, so if you plug in 2 to what equation?
The
Derivative, right? So if you plug in 2 into velocity, you get 0 for velocity. So yeah, there's different ways to think of it. Maybe the easiest way to think of it is velocity changes from positive to negative. This can be tough, okay, to understand, but we'll give it a shot here. Melina, see if you can follow this. Like, okay, I'll try to model it. I start at time t equals 0 on the bird. What do I do? What's the first thing I do? Like, look at the pictures and the graphs and all that, see if you can figure it out.
You fly up.
I'm not flying at all.
Oh.
So this is motion on the branch. I don't leave the branch.
okay.
Did you watch the video?
Yeah.
That bird is like moving sideways, right? So, okay, what direction should I go? Right, left? What am I doing?
The right.
Good, right. So the positive position, right? The position goes from 0 to positive numbers, right? So here, I'll try to model it. All right. So it's like, I move to your right. And what should I be doing?
Your moonwalk.
Huh?
The moonwalk?
Oh.
Oh.
Alright, so I do a little moonwalk, but then what happens? Like, just describe the motion to me. Take the
Um,
whole motion. Okay, I
okay.
start at 0, I
And
move to the right.
Move to the right.
What's that?
You move to the right, and then once you get to t equals 2, at your peak, and then you move back to the left.
Oh, okay, so then I start moving back to the left.
Yes.
Alright, would I go past position 0 or
Yes.
not? Or yeah, right. And I end up at position...
-5.
Yeah, that's right. I think that's a good description overall. So just to recap, start in the middle, move to the right a little, come back to the left more, so I end up like further to the left than I started. Yeah, good, I like it. I think that's a good one. So then, okay, what is the position of the bird when it changes directions? Austin? Yeah, good, like S of 2 equals 4. So its position is like 4 units to the right of the middle or something like that. Alright, yeah, that's fair enough. So it changes directions once it reaches that rightmost point. Okay, I'm into that. Everts. Where's Everts? She out today?
She's right.
What?
She's right there.
Oh yeah, that's right. Oh, I forgot that this is all on video. You got that sweet dance going on.
Yeah.
Wait a minute, now we gotta go back. Wasn't I like talking to Simo about like whipped cream?
Yeah.
What?
Did I say anything inappropriate at any point? Is everything nice? Everything is
You
alright?
said that you were gonna fight me.
There was like a math fight though, right? Oh wait, no, it's just...
6:30.
I meant like a math fight, you understand, you know? Like, you know, quick factor this problem, 5 seconds, and whoever wins, like that kind of thing, you know what I mean?
Yeah.
Yeah, we're all good, right? You didn't feel threatened or anything by me? Okay, that's good. Alright, Curtis, I got a question for you. Over what interval is the bird's velocity positive?
0 to 2.
Ooh. Yeah, I like it. You can kind of just see it. Alright, would you say 2 is included or not included, or what? Alright, what is the bird's velocity at time t equals 2? Is 0 positive? I'm gonna go with no. Zero is like unsigned. You know what I'm saying? No sign. So yeah, that's a big old no. So over what interval is the bird's velocity positive? We would say it's positive on the interval from 0 to 2, but not including 2. So if you were never good at interval notation in pre-calc, then you should start getting good at it. Alright, so it'd be like that.
So why is 0?
Because it is.
Oh, I see.
Yeah. Now, see, now I'm all self-conscious about this video, because these answers sound ridiculous, like when you just say them out loud. But you guys know what I mean, like Jess, you know, why is 0 included? Because it is. Thanks, Mulvey. Well, like, you get it. Like, you know where I'm coming from.
I got it.
So it's good. All right.
Why?
So, yeah.
I forgot, why is the 0 in like a different bracket, in the bracket? And
The hard bracket
Yeah.
means to include 0. In other words, what is the at time t equals 0, does the bird have a velocity at all? The answer is yes. Like you're sort of catching the bird, we're sort of like starting to see the bird after it's already been moving. So at time t equals 0, its velocity is 2. That's what the derivative graph says. Oh, 4, I'm sorry, I'm saying that wrong. It's 4. The velocity is 4 units per unit of time or whatever. And so, yeah, that's the answer to your question. Alright, let's see, Simo. What's the deal, like, what's the interval for which the velocity is negative?
Is it like 2 to 5?
Yeah, good, but not including 2 again. Yeah, I'm into that, I'm totally into that. Okay, so let's see, bands, where's bands? What does negative velocity mean? What does it mean?
Moving backwards.
Yeah, good. Okay, so specifically, in the context of this problem, what does that mean?
Moving to the left.
Correct. Very, very good. Bird moves left. Yeah, you get it. I'm getting some good answers. Yes, Maggie.
What, I thought it was, like, slowing down if I moved back from the other
this whole slowing down thing, yeah, I mean, there's some issues here. Here. Alright, Maggie, I would say that the bird is slowing down on this interval. That's my opinion. Okay, slowing down. Alright? So velocity is positive on the interval, but decreasing. And eventually velocity reaches 0, at which point the bird's not moving. So slowing down. Maggie, what would you say in terms of slowing down or speeding up? You see me tracing this, the curve. Like, would you say the bird is slowing down or speeding up? I agree. It's moving to the left, but it's speeding up, right? Did you have a question? I don't even remember.
That was my question.
Are we good? Alright, let's roll it. So I got news for you. The speedometer in your car gives the speed of your car. Yeah! True fact. You might not have known that, alright? So actually my own speedometer is kind of like makes me upset. So I got this different car last year. My old one like broke down. And I have one of those speedometers that just gives you the number like large. It's an old Honda Civic. And so like instead of a dial, it just gives the number. So you can imagine like I drive my kids around. It's always like, Daddy, why are you speeding? You know, like they can just see the number. But Daddy, the speed limit sign says 30 and you're going 33. So why are you going 33 when the speed limit is 30? It's like, shut up. You know, like that kind of thing. So yeah, I really don't like it. And I think you can see it from outside the vehicle too. So just be aware of that. Anyhow, I drive very safe speeds and everything's like good and under control. I don't try to break laws and do bad things. But I'm just saying, like occasionally you're probably going to go a little bit over here and there. And like, yeah, my kids can just see it all the time. It's kind of irritating. So anyhow, but this is true. This is a true fact. So the speedometer gives you the speed. Yeah. Now, technically, speed is the absolute value of velocity. So now you guys are experienced enough, you should be able to read a sentence like this. So read it. Does it make sense to you? Speed is absolute value of velocity. Just today we've said that velocity is the derivative of position, right? The instantaneous rate of change of position. So then the absolute value of that should be that. That's just another way of saying the same thing. Rate of change of position with respect to time. Okay?
I think they have to use S, because normally we would use X.
Yeah.
And that should be like the SDT is too common.
We often do that though. You'll see later. So those are sort of the two popular ones. It's S as a function of t and then X as a function of t for motion in the x-axis. Like we actually did this if you remember pre-calc with parametrics. We had y as a function of t and x as a function of t. In calc 1 we don't deal with the y dimension for motion. We deal with only like one direction for the most part. So then x is a function of t. Anyhow, let's do some math. So I guess what I'm trying to get you to see is these are two graphs of the same object in motion. Okay, so they are. It's, in other words, this is capturing the same scenario. Griffin's not around. Volk, you're up. Okay, so this is a velocity graph. So watch my pen, and then you tell me, Volk, what direction is, let's say it's a particle. What direction is the particle moving right now?
To the right,
Right is correct. Why did you give that answer?
because it's positive velocity.
Yeah, because the velocity is positive. All right, I'm into that. Norman, on this interval, watch my pen. What direction is the particle moving?
To the left.
Left is correct. All right, keep watching my pen. On this interval, what direction is the particle moving?
Back to the right.
False. All right, and now many, many people in the room will probably think the same thing you're thinking. This is very confusing at first. Because you look at a function that's increasing, and you want to say something about right, but it's not correct. All right? Volk, can you give me a reason why the particle is moving to the left on this interval?
Because it's still like the negative velocity.
Yes. This is very hard to grasp at first, but this is what today is about, is trying to get all this sorted out. So, yeah, if you think about it here, we could say specifically that the velocity is -3 normal. So in other words, things move into the left at, say, 3 feet per second or something like that. Now here, the velocity is -2, but it's still negative like Volk is saying. So the particle's still moving to the left, but then Maggie, we get back to what you talked about slowing down or speeding up. So Maggie, from here to here, would you say that the particle is slowing down or speeding up?
Speeding up.
No, its velocity went from -3 to -2.
So slowing down.
So it's moving to the left, but less fast. You see what I'm saying? so slowing down. And all this can be very confusing at first. Now, go over to this graph and it's a little easier to see, because this is just speed, which is the absolute value of velocity. So here, the particle is speeding up, because the speed is increasing. And here, Maggie, same interval, the particle is slowing down, because the speed is decreasing. Alright, let's see, Randy, let me see how do I generate this speed graph? I use WinPlot, first of all. It's this sweet graphing technology. How did I get this graph?
You just found the derivative of the position, like...
Oh, here, let me start over. I used this function to generate that graph for velocity.
Alright. You just got the absolute value on it?
True life. So how do I generate the speed graph? Like that. Yeah, good. What was the greatest velocity achieved and when did it occur, Caroline?
The greatest velocity was
-3 is a very small number relative to some other numbers. When we say greatest, we mean greatest, numerically. Think of the greatest number.
Oh, so 1.
1 is correct. When did it occur?
At 0 and 3.
Very good. Very good. And Aaron, what was the greatest speed achieved?
3.
3 is correct. So, yeah, there's that issue. So it was a negative velocity, but the speed is positive. So 3 is the greatest speed. 3 feet per second or miles per hour or whatever you like. Okay? And Aaron, when did this occur?
T equals 2.
Anybody with a math question? Yes?
I don't get 4.
Problem 4, what was the greatest velocity? I can show them to you. The largest number, think of the numerical value of the velocity function. Its largest numerical value is 1. 1 is greater than -3. Like it's further to the right on the number line. In other words, any positive velocity is greater than any negative velocity. Which is a weird thing to say, but it's sort of true. It's true in an unsatisfying way. This is the one that we think of in common experience, you know, like speed. We think of the motion of objects in terms of speed, not so much velocity. But this is calculus, and you need to be comfortable with the technical aspect of it. So a falling object, for example, Peters. Falling object, positive or negative velocity?
Negative.
Yeah. Get it? Like that. Alright, I got some sweet homework for you. Let me get your schedule out. Got some work to do. Class about to end. Perfect timing then. Alright, that just looks like a bunch of happiness. Anybody absent? Huh?
Jess.
Oh, Griffin, yeah.